So let me remind where I stopped. So I mentioned the result by Campana-Peternel, which combined with the definition of canonical singularities gives characterization of unruled foliations. So F of canonical singularities. Then F is unruled. KF is not pseudo-effective. If and only if F is unruled. So then I briefly mention fun foliations. Perhaps I will say a few words now about them, more precisely than I was in the morning. Again, this business starts with the study of singularities, with the study of symplectic singularities, and a conjecture that Beauville made while studying symplectic singularities. So we say that foliation F is funnel. If KF is ample, and the first question that you can ask is what are the possible index of KX? So we can always write, minus KF as an integer, IF times L. Well, L is ample and primitive. So to make things simpler, I will be working off of a projective manifold. And then Araújo, Carolina Araújo, Stefan Drouet, and Shandor Kovacs proved that this index is at most the dimension of F, and they proved that also that when the dimension is equal to, when the index is equal to the dimension, then X is Pn, and F is given by a linear projection. And then Carolina and Drouet pursued the classification or the study of foliations with IF equal dimension minus 1 and also dimension of F minus 2. So they call this Del Peso foliations, and the ones below, Mukai foliations, for obvious reasons. And there is also work by Andreas Horing on the same subjects. They also these authors and also these, they allow some mild singularities in some cases. The codimension 1, the results are more complete. They have also results in arbitrary codimension. It's a very rich subject, but apparently the complexity of the subject is growing quite fast, and it doesn't seem, yeah. I just want to mention that there are people working also in the funnel case. So what I want to discuss this afternoon is foliations with KF, canonical bundle, numerically trivial. So there are some previous results on there are a couple of people work on that. So let me just list some names. There's the work by Cerveau and Lins Neto, motivated by the study of foliation. So they studied the case where x is equal to P3, and codimension f is equal to 1. Dimension 1, it's quite easy indeed. More or less, at the same time, there is work by Polishuk, who was interested in x equal to P3, codimension 1. But his motivation comes from Poisson structures. Indeed, these objects, foliations with canonical bundle of dimension 2, with trivial canonical bundle of dimension 2, are example of Poisson structures. And also motivated by the study of Poisson structures, there's a work by Stéphane Drouel who deal with the case of dimension 3, and F is smooth. No assumption on X, except for projectivity. And smoothness, of course. So through all my talk today, the ambient will be smooth. I will be talking all the time about projective manifolds. I will not insist on that. So it's projective manifolds all afternoon, unfortunately, of course. Okay, so I think that the first indication that there is some structure theory for these objects comes from this theorem of Drouel, which was generalized by Touzé without knowing about Drouel's result, because this one is in dimension 3, and this is in any dimension. So F codimension 1 is smooth. Then if the KF is numerically trivial, then we have, then after a finite étale covering, we have one of the following possibilities. So case A is just F is an isotrivial or isotrivial vibration with fibers with numerically trivial canonical bundle, or so let's with do you have a good name for varieties with numerically trivial canonical bundle, which it's not Calabi-Yau? Don't want to enter in conflict with your terminology. Okay, why not? So B, a suspension of representation from P1 of B to automorphisms of P1, where B is numerically Calabial. And, or C, X is a product of a torus, abelian variety, times Y numerically Calabial, and F is the pullback of a linear foliation. Perhaps let's say an easier way. And F is defined by omega in H0 A omega 1A. So I think that I don't need to say anything more about isotrivial fibrations with numerically Calabial fibers. Here, by a suspension, this is a usual construction in foliation theory or in dynamics, is that when you have a representation of the pi1 in automorphisms of P1, you can construct a pi1 bundle and a flat connection along a flat connection on this pi1 bundle, P1 bundle, and the horizontal sections will be the leaves of the foliation. So this is come from a connection. And in this case, also, I think that's clear. Okay? So although they have essentially the same result in dimension 3, the proofs are very different. So the proof of Stéphane of Drouel is based It's a numerically Calabial manifold. So X, so from this, you have this construction of, let's denote by this, which is essentially, you take the universal covering of B, you take P1, and you make pi1 of B acts here, diagonally. In the first coordinate, you act by deck transformations, and in the second coordinate, you act via the representation. And so you have this action, you take the quotient, and you have this, you have X. And this quotient comes with a natural foliation. Here on the universal covering, you have the projection on P1, which gives a horizontal foliation. And I'm doing these identifications in such a way that everything is preserved. And if I start, this is just, I can also interpret this as a flat connection on a rank 2 vector bundle, and I'm taking the projectivization after that. On a rank 2 vector bundle with a flat connection. Okay? So this is this. And so F is the suspension. We say that F is the suspension of B through rho. So the leaves are not, attention that the leaves are not necessarily compact. The leaves will be quotients of the universal covering of B. Okay? So the strategies are very different. Drouel restricted himself to dimension 3 because he uses usual Morris theory. And Touzé essentially used some of the results that we discussed this morning and others. So the strategy of Touzé is really sketchy. The first thing is to note that H1 of n star F is H0 Px tensor n star F. And it's the usual game of Serre duality and Hodge duality. Very similar to the kind of game that Stefan was playing in the previous talk. And what happens is that when H1 is 0, then the conormal bundle is numerically 0. So essentially, you end up in a Calabi-Yau, in a numerically Calabi-Yau manifold. This is just because the bot class lies in H1 and star. The point is that when you're looking at foliations, you have a natural connection on the, not a connection, but you have a natural partial connection on the tangent bundle of the foliation, which somehow measures how the things are varying transversally. This is a classical construction of bot. And you get some class H1. This connection gives rise to a class in the H1, whose imaging omega 1 x will give the Chern class of the vector bundle, in this case, of the line bundle. Okay? So if it's not 0, we have essentially two possibilities. Either, so we produce a V in H0 x Tx tensor and star F. And I can always take omega in H0x, omega 1x tensor NF, defining F. And the contraction of both will be a global section. So we are in this very interesting situation. This guy, N star F, is just the canonical bundle of X. So we are in a very nice situation where either this thing is non-zero, and I'm providing a splitting of the tangent bundle, or V is tangent to F. Okay? So essentially, the picture similar to what you see when you're studying Calabi-Yau varieties appears. You have a splitting of the tangent bundle, at least in one of the cases. And then we can make use of a theorem by Brunella, myself, and Touze, which says that if I have X as move, projective, and Tx splits as a sum of Tf plus L, with rank of L equal to 1, then the universal covering splits okay? And of course, this is P1, disk, or C. So when the tangent sheaf of the manifold splits, we have no difficulty to construct a metric on Y. So Touze constructs a metric on X tilde, and hence on X, which is Ricci-Flat along Y. And he uses differential geometry of complete Ricci-Flat manifolds to arrive at the list. In the other case, you have to prove that you end up essentially in a torus. I don't want to enter in the details here. But essentially, these are the main ingredients. Then he used differential geometry, Ricci-Flat metric. So this implies the existence Ricci-Flat metric on leaves. And we can use differential geometry, results by Gromov and others. So differential geometry of complete ridge flat manifolds, because we are working at the universal covering. Very nice, but very hard to apply in other situations, because ideally, in this situation, you would like to construct a metric on the ambient which is ridge flat along the tangent sheaf, and you cannot do this in general, unless you have some Keller-Einstein property of Tx or things like that. But in general, you don't know how to do that. Here, use this structure. Of course, we could hope, and indeed there is a problem by Beauville that says that whenever we have a splitting of the tangent sheaf or tangent bundle of a manifold, the universal covering should split, and you can, in this case, you can construct a metric which will respect the factors, but we are very far from knowing anything like that. Very well. So what next? Anyway, the nice thing about Touzet's results and his techniques is that allow us to obtain a very strong rigidity results for foliations with a numerically trivial canonical bundle on projective manifolds, but only for, in general. Assuming that the canonical bundle of X is pseudo-effective. So X is not uniruled. So in this case, if F has Kf numerically trivial, then F is smooth. And the tangent bundle of X splits. Where G is another smooth foliation. Okay. This is, of course, quite useful. In particular, just reduces the problem of understanding foliations of codimension 1 with numerically trivial canonical bundle to the problem of understanding these objects on uniruled manifolds. But before pursuing this line, and let me just say one word about the proof. The proof is essentially what Stefan explained to us, the splitting, the Bogomolov's splitting argument. Of course, you have to use some new ingredients. The point is that there are two ingredients. First is the fact that when you can write some metric which has good properties from the pseudo-effectiveness of Kx, and then you can produce a QQ form from that, Q, the codimension of F, which will be closed by an integrability result of Demail. Because Demail proves that subbundles with, in this case, this foliation is subbundles of Tx having this property are automatically integrable. This is a result by Demail, which one forms with coefficients in anti-pseudo-effective bundles are automatically closed. In the proof of that, he proves essentially this extra ingredient. But then you do the same kind of game to prove that, to produce this splitting. Okay? And then if we are very, very optimistic about this picture that should be somehow similar to the case of varieties, we should perhaps try to look at the simplest possible case and try to understand X projective manifold with Kx pseudo-effective and F, a foliation on X with C1 of Tf equal to C2 of Tf equal to 0. So if we don't, we ask not only that the canonical class is numerically trivial, but also that the second Chern class is numerically trivial. In the case of varieties, this essentially characterizes a billion varieties. So up to a tile covering, you have a billion varieties. But somehow, surprisingly, here it's not the case. So the conclusion then, the conclusion is that we cannot prove that that a billion variety splits here somehow, but then what we can show is that there exists F from X to B with a billion general fiber this is a quasi-fibration, and F is tangent to F. So the leaves of the foliation F is tangent to this. We would really like to have a map like this, which is a morphism and which is isotrivial. But we cannot guarantee. There are examples. Perhaps it's very, I believe that this map can be, is probably a submersion, we don't know. But there are examples, essentially due to faultings, which shows that F can be non-isotrivial. For F of codimension with codimension at least 3. So in codimension 2, then we can show that up to a finite tile covering, I guess that there is also an up to a finite tile covering here. I didn't wrote. Cover. X is a product of a billion variety times some Y. Okay? And so only to have an idea what kind of techniques we have to approach something like that, let me give a sketch of proof of this result. I will just say a few words. I will not sketch the proof. I think I will concentrate on the case of codimension 1, in the singular case. So the idea here is very simple. It's just we have to use, the idea is simple, but we use deep theorems. So the first thing is that you have Donaldson, Uhlenbeck-Yau gives a unitary connection on TF. That's our assumption, C1, C2, TF equals 0. And then this TF in the decomposition of this previous theorem is essentially the normal bundle of the order foliation. So I have a unitary connection on the normal bundle of the order foliation. And so essentially, because of that, we can prove by hand that the universal covering of X is a product. So it's a product Cn, C dimension of F, times Y. Okay? And from the unitary connection, we not only get this metric information, which is useful in the universal covering, but we also get a representation from pi1 of X in un. And this representation essentially is the obstruction for the existence of a universal, of a finite tile cover where the variety splits. So either this representation has finite image, so after finite tile covering the variety splits, or we can show that it has some simple factor. There's a risky closure of it, has some simple factor, and we can use theorems by Zuo, which were clarified by Benoît Clodon, Campan, et Sidieu. That says that Zariski dense representations on simple groups, factors, they factor through varieties of general type. And I guess that this one, the kind of, the prototypical kind of result that Stephans would like to make work also in the KLT world. But very good, so something like that is essentially in contradiction, we will enter in contradiction with the existence of these C factors. And so the point is that unless the C factors are tangent to the fibers of this map to a variety of general type. Okay, so that's where you produce this fibration. Okay. Very, very good. So let's go on. And let me state what we know about codimension 1 foliations with numerically trivial canonical bundle, but now without assumption on the singularities. So F, codimension F equal 1, KF numerically 0. And let's assume that F has canonical singularities. Otherwise, we know that F is unruled, because if it's not canonical, it will have a model where the canonical is not self-effective. Because here, this is not an assumption. If you want, it's even a conclusion. Otherwise, F is unruled. So the conclusion is that F, we have two possibilities. F is an isotrivial fibration. Or after étale covering, F is defined by closed rational one form without zeros of codimension 1. So perhaps I should say a few words about the statement, because Previously, we were giving these very nice geometric descriptions of the foliation. So it's a suspension, or it's linear on a torus. And here I'm just saying, well, it's defined by a closed relational form. But the point is that for foliations, this is extremely special. So you somehow should think that this property of being given by a closed rational one form, perhaps in some covering, is exactly what you have after being a fibration. So if you somehow make a hierarchy of complexity of the dynamics of the complexity of foliations, simplest kind, dynamically speaking, are fibrations. And then the next simplest case are foliations defined by closed rational one forms. This is very, very special. Okay? Unfortunately, trying to link with the discussion that we are having this morning, there is still one kind of embarrassing gap in our statement, is that we do not know yet we do not have a proof. We know, but we do not have a proof that KF is torsion, which of course you expect. And I also believe that this should not be the optimal statement. I guess that it's possible to get much closer to the picture that we have in dimension 2. Because remember, in dimension 2, Kodaira dimension 0, you have some contraction to some KLT spaces, a quasi-atomic cover, which was defined by a global vector field. Here, I think that it's possible to arrive, in this case, to something which is very, very close to be defined by an action. But time will tell if I'm right or wrong. But anyway, let me just give. So essentially, all the things that we have done before fails. We have nothing that, none of these methods that we have tried to do this works. But there is one possible very quick and dirty, or quick strategy to prove that. So quick conjectural proof. Meaning that I'm going to give a quick proof which depends on some very tough conjecture. So the point is the following. It's based on considering the reduction mod P of F. So this means that we are just presenting F and the variety and everything that's involved in our problem in a finitely generated Z algebra, taking a maximal prime and ideal and reducing everything this maximal prime ideal to obtain something in positive characteristics, even over a finite field. And so this thing behaves very different. Vector fields and foliations behave very differently in characteristic P. Frobenius does not hold. You can have some involutive distribution. This is a property which is preserved by reduction mod P, which has no leaf at all. Through any general point, there are no formal neighborhood of that point where you can write your foliation as a relative tangent bundle of a fibration. But the point is that it's very easy to understand where the failure to the existence of leaves is. This comes essentially from the fact that TF, we have a natural map from TF to TX that takes a local section, V, and sends to the pth power. Written like that is not very correct. So to make it all linear, we do a pullback by Frobenius and mod out by TF. So this is a kind of arithmetic O'Neill's tensor. In the same way that we have this map that measures involutivity in characteristic 0, we have this guy that measures this P closeness in characteristic P. And if this map is 0, then F is a fibration. F admits first integrals on characteristic P. But the thing is that this is not very useful, because these foliations in positive characteristic are quite temperamental. Either they have no leaf at all for a general point, or when they have many. You don't have a meaningful notion of the leaf, because you don't have a meaningful notion of first integral, because if you have f, a rational function, contains TF. So if I have some function which is constant along the leaf, this would be the algebraic formulation of that. From a rational function, I can produce a subsheaf of the tangent bundle, a kernel of df. And if the tangent bundle of the foliation is contained on that, it's in characteristic 0 is to say that this function is constant along the leaves. But the point is that if you're in characteristic P and you have something like this, it does not make any difference if I just add some p powers and do whatever. So the kernel do not change. And of course, the level sets change a lot. So we don't have this notion of a unique leaf passing through a point, but you have many leaves passing through a point. But anyway, there is this conjecture, which is quite deep, by Ekedal, Scheffer-Baron, and Taylor, that says that if F is P closed for P in U dense and open, U contained in spec R, dense and open, then F has first integral, F has algebraic leaves in characteristic 0. So let's just slightly change the notation, take a reduction mod P of F and call it Fp. So P is a prime. So P is a prime, and this is spec R. R is the Z module that everything is defined over. And so F, the original F, has algebraic leaves. But of course, this conjecture is extremely hard. It's indeed a nonlinear version of a linear conjecture, of a conjecture for connections, a linear version of it due to Grothendieck and Katz. So it's very, very hard to be able to apply that. But the point is that in this case, if we believe in this conjecture, we would reduce our problem to understand when it's different from 0. So when this map is different from 0. So if phi p is different from 0, then there is some very nice results by Miaock and Scheffer-Baron that says two things, that the image of phi p has degree of the form m plus m times degree of canonical of f. f or something like that. And on the other hand, we also have that the degree of the image of phi p is congruent to the degree of nf mod p. So here, of course, degree, I mean degree of a sheaf. I'm just considering the degree of its first-gen class with respect to some polarization. And the point is that this turned out to not to be extremely useful in general, because there is a p times here. Because there are the appearance of this factor of p here. But in the case where the degree is 0, you don't have 3 times something. You don't have this p. Oh, sorry. So it's plus p, something like this. So in the case where the degree is 0, this p does not appear. So we have everything is bounded, and you can lift this information to characteristic 0. And you can prove, indeed, that locally, if I take a one form defining the foliation, omega f over vp is equal to 0. So essentially, this will allow to produce v a section of the normal bundle such that, or at least p for every p. And using these two results, we can lift to characteristic 0. Very good. Of course, this is not satisfactory, because under this assumption that this guy, so if phi p is different from 0 for a dense set of primes, we have the theorem, we have the result. But if not, if it's different from 0 for just for a closed set of primes, we don't know how to apply this conjecture, but somehow we gain something. Because from the 2Z results, we know how to prove the theorem when the foliations is moved by inspection from the list that he gave. So essentially, we can try to understand singularities of f. But now, p closedness for almost every prime plus canonical says that at least locally, outside Z of codimension 3, this foliation is something like it's just the differential of some function. So the foliation will be given, is essentially monomial, like this. Okay? So this is essentially, it's a simple computation due to McQuillan in dimension 2 that we can generalize to codimension 1 by classifying canonical singularities in codimension 2. And now the nice thing is that we can go back to the original strategy of 2Z. And, oh no, we need another ingredient, sorry. So we need another ingredient. So the extra ingredient, now that we know how the singularities, if the theorem is not proved yet, we know how the singularities of the foliation are. And so we have another ingredient is to look at the deformation of free rational curves. Of course, along the foliation. And then essentially we have this dichotomy. We can try to take a general rational curve and we can try to look how the cotangent bundle or the tangent bundle of F looks like when you restrict to C. Since the determinant of TF is trivial, there are not many choices. So either you have that this thing is trivial, or we have that it has some positive factors. Or it has some positive factors. So suppose that C is not F, is not contained in a leaf of F. Plus something negative. So you have something positive plus negative, right? Ample plus something. Okay, so let me just, since my time is running out, let me just say how this thing goes. When you have this trivial case, you are able to somehow, together with this normal form of the singularities, you are able to prove that the foliation indeed is smooth, because you are going to give, just keep at it. And let me just show what you do in this case, because it's very close to this Bogomolov-McQuillan stuff. That I forgot to mention that indeed there are some gaps in the proof that were filled by Quebecus and his co-authors, Toma and Solacondi, I think. It's, if it's not, then the foliation is smooth, and since falls in to the first result. Okay. So what we can do in the ample case, we can do the following. Let's just look at this picture. You have C, which is just a P1. That's not, it's important. And we can try to look the graph of the inclusion on X. And the point, we do just like Bogomolov-McQuillan do. Through each point, you put the piece of leaf of F through X in C. So the point is that if this curve is general enough, does not pass through the singularities, is not contained in the foliation, you are going to obtain something which is smooth. You're going to obtain a germ of smooth variety of dimension n. So Y is a variety of dimension n, a germ of analytic manifold of dimension n. And so the point is that the normal bundle of C, or of delta, inside of Y is essentially the tangent bundle of F, restricted to C. And we are saying that we have these positive factors and these other factors which are either 0 or negative. But the point is that this presence of these positive factors allow us to construct deformations of this curve which will stay inside this Y. So the deformations of this curve, tangent along the foliation, are precisely the deformations of this curve C, or this curve delta, which stay contained in Y. And if we have these ample factors, we can construct a deformation which passes through a point. But now, if you have, there is this lemma, probably well known, but it's kind of nice. So if you have this deformation of curves which pass through a fixed point, it's automatically algebraic. Because what we are doing, we are looking at the space of morphisms. We are asking the morphisms that pass through that point. We are asking the morphisms that has tangent space containing the tangent space at that point, and so on, high and high order. So we have just you have just algebraic conditions, one over the other, and by Nustellensat, we get that this is an algebraic set. And from that, you can do bend and break. Once you have constructed this deformation, you can do bend and break to produce rational curves contained along the leaf and deduce that F is univocal. So this is the easy case. The hard case is this one. But we need to do a lot of intermediate steps to arrive at a situation where we prove that H1 n star F is different from 0, and we can prove the smoothness of F. Okay, so that's more or less what I like to talk about. I don't think that we have the right approach. Somehow it says that there are results, there are structural results, but the proof is not satisfactory. It's too convoluted, and really doesn't share any light in this. But that's what we have so far.